All right, section 4.3 is monotonic functions in the first derivative test. Monotonic just means increasing everywhere or decreasing everywhere. Okay? So in the interval from A to C2, this graph would be monotonic because it's increasing everywhere. Do you see that? From A to C2. Okay. Here is the corollary 3. Says suppose f is continuous on a closed interval, differentiable on an open interval. Those two go together. Says if the derivative is positive, that's what this means. If the derivative is positive for each value, then the function is increasing. So anytime the derivative is positive, the function is increasing. That means it's going up as you move from left to right. If the derivative is negative, then the function is decreasing. That means it's going down as you move from left to right. That's basically all this says, and we've known that for quite some time now because we've been looking at the derivative as a slope of a tangent line. And if the curve is going up as we move from left to right, then this derivative is going to be positive because any tangent lines right here are going to be increasing lines, right? Even if it's a horizontal at some point, this function's going up, right? Okay. If the derivative is negative, the function is decreasing. Well, that kind of makes sense. Here's the derivative being negative because the function is going down as we move from left to right. Okay? Makes sense? Looking at a picture. So increasing, here to here, here to here, here to here, and decreasing. Okay, that's where the derivative is negative. Okay? Where the function switches from increasing to decreasing, we have what's called a local max. That's where the function switches from decreasing to increasing. Just because the derivative is equal to 0, though, doesn't mean that we have an extrema. Anytime the derivative is equal to 0 and the derivative goes from positive to negative, we have a local max. If the derivative is undefined, that's a critical point. Remember? And here the derivative is equal to 0 and it's no extrema. But right here, the derivative is undefined. This is a critical point. And this is a critical point. But notice your function went from increasing to decreasing. It went from positive to negative. Oh, right here, if we go from negative to positive, then the function has a local minimum. Okay, right here. All right, so
why is it undefined for that?
This is undefined right here because we have a corner. Remember, the derivative does not exist at the corners, at sharp corners. Okay? Good question. Example 1. Answer the following questions about the functions whose derivative is given below. Here's the derivative. What are the critical points of this function? Critical points, remember, are where the derivative is either equal to 0 or undefined. Critical points occur where the derivative is either equal to 0 or undefined. So where are our critical points going to be here? At x equals -6 and x equals 4. All you do is you set each one of these factors equal to 0. This is why we like having everything factored. That's why I was, on the test wanting to know how to get everything factored properly, because I knew this was coming. Then the question is, on what intervals is f increasing or decreasing? Well, all I need to do is find out where is this derivative positive or negative. Do y'all remember doing something in college algebra where you checked to see where a function was positive and negative by dividing the number line into intervals? Yes? No. Well, you remember in calculus doing this. I have 2 critical points, right? I can use those critical points to divide this number line into intervals from negative infinity to negative 6, from negative 6 to 4, and from 4 to infinity. Now, the sign of the derivative everywhere in these intervals is either going to be positive or negative. Because if you have a critical point, that's where your function switches from increasing to decreasing, maybe, right? So what I need to do is pick a test point. Any number in here will work in this interval from negative infinity to negative 6. So we're going to test x equals negative, I like 10. Y'all like 10? Negative 10? Yeah. To check the sign of the derivative. Okay? If x is equal to negative 10, this first factor is going to be positive because it's squared. The second factor is going to be negative because negative 10 plus 6 is negative. And so the entire value of the derivative here is going to be negative. This is the sign of the derivative. Okay? And then what does that tell us about the shape of the function? It's decreasing, it's going down. Because we said that if the derivative is negative, the function is decreasing. Alright, so from negative 6 to 4, we need to pick a test point. What do you want to test?
1.
You can test 1. I'm going to test 0 because the arithmetic is easier. 0 squared is, negative 4 squared is positive. And 0 plus 6 is positive. The whole thing is, so what is the function doing? The function is increasing here. What does that tell us about the point x equals negative 6? It's a local minimum because it goes from decreasing to increasing. That shape is a local minimum right here at x equals negative 6. Go to the next interval. What do you want to test? 10,000. It's in there. All I got to do is pick any number in that interval. A billion. A billion minus 4 squared is a really big positive number. A billion plus 6 is a really big positive number. The whole thing is, what's the shape of the function? Increasing. So, excuse me. Knows I'm in class. Alright, so to answer part B to this, we use this chart here. It says on what intervals is f increasing or decreasing? To answer B, f is increasing on the intervals that go from negative 6 to, it's not, yeah, I guess we could say from negative 6 to infinity. Okay? And then f is decreasing on the interval from negative infinity to negative 6. At what points, if any, does f assume a local maximum and minimum value? Well, we already addressed that just by looking at this. Can't you envision something that's going like this? And that would be a minimum. So we have a local minimum at x equals negative 6. We don't know the function, we only know the derivative, so I can't give you a y value. I can just tell you where that minimum is going to occur. Any questions about this problem? No?
Like if you didn't want to put the infinity beside the negative 6 on the end.
Well, I was thinking, do we have to discount that 4 where the derivative was equal to 0? And no, we don't, because it was just asking about where's the function increasing, not where's the derivative positive.
So what is happening on that point?
That is actually going to be a point of inflection. Look at this graph right here. You see this point where the derivative is 0, but there's no extrema right here? We're going to get to that eventually, but that's what it is. All right, the first derivative test for local extrema. This kind of formally states what we just observed. If the derivative changes from negative, that's a decreasing function, to positive, that's an increasing function at C, then f has a local minimum at C. Well, that makes sense, right? If the derivative changes from positive, which is increasing, to negative, which is decreasing, we have a local maximum at C. If the derivative does not change signs at C, which is what you were asking about, that is, the derivative is positive on both sides of C or negative on both sides of C, then we say that it has no local extremum at C. We're going to discover later on what that point may be a point of inflection. Okay? Just kind of giving away the ending here. Example 2 says find the local extrema, the intervals on which the function is increasing and the intervals on which the function is decreasing. That's the same thing we just did for the first one, right? So we begin with, there's the function, we begin with the derivative. F prime of x. How do I find the derivative? What rule do I use? Product rule. So this is going to be the first times the derivative of the second plus the second times the derivative of the first, 3/5 x to the negative 2/5. Excuse me. So I have an x to the negative 2/5 that I can factor out. And when I pull a x to the negative 2/5 out of x to the 3/5, that leaves behind an x plus, I can do this over 5 because I have a 3/5 here. That leaves a 5x plus x 3 times x plus 1. If you factor out a denominator and there's no term like that, you just multiply it so that when you can check your factoring by distributing. And if you were to distribute this term right here back through to these, you would get what we started with up here. I'm going to take all these marks off because it gets confusing. But try distributing, and you see that we end up with x to the 3/5, because that's x to the first times x to the negative 2/5 is x to the 3/5. And dividing by 5, multiplying by 5 cancel each other out. And then there's our 3 divided by 5, x to the negative 2/5, x plus 1. So our derivative then is going to be equal to 5x plus 3x is 8x plus 3 over 5x to the 2/5. I wanted to do this because I needed to find my critical points. So now you have critical points where the derivative is either equal to 0 or undefined. This derivative is equal to 0 if the numerator of this fraction is 0, correct? The only way for a fraction to be equal to 0 is if the numerator is equal to 0. So that's going to be at x equals negative 3/8. That's where the derivative is 0. or we have a critical point at x equals 0. Because at x equals 0, this function is undefined because that's where the denominator is 0, right?
Yeah.
So these are two critical points. So now, to figure out where the function's increasing and decreasing, I need to do my sign chart again. So grab this because I like straight lines. Once again, I have two critical points. My intervals are going to go from negative infinity to negative 3/8, from negative 3/8 to 0, and from 0 to infinity. Once again, pick your test points. How about x equals negative 1? Will that work?
Yeah.
Sure it will. If x is negative 1, I end up with negative 8 plus 3, that is negative, over, this is squared, isn't it? Because that numerator's the power, the denominator's the root. So that denominator's always going to be positive. The whole thing is negative. That's what the sign of the derivative is. And then we look at the behavior of the function. If the derivative is negative, the function is decreasing. In the next interval, we can test x equals negative 1/8, can't we? Sure. 8 times negative 1/8 is negative 1 plus 3 is positive, divided by the denominator is always positive because it's squared. This whole thing is positive. And what does that tell me about the behavior of the function? It's increasing, right? If the derivative is positive, the function's increasing. Go to the next interval. What do you want to test? 1 works, right? Isn't that going to be positive as well? You get a positive over a positive. The whole thing is positive, so that means that the function is, once again, increasing. It's just a happy coincidence that this shape was the same. I did not do that by design. So, we found the local extrema. It looks like we have a local max, not max min, at x equals negative 3/8. And the function is increasing from negative 3/8 to infinity, and the function is decreasing from negative infinity to negative 3/8. That's a lousy infinity. A little better. Any questions? Try not to make your infinities look like 8s. Okay. No questions. Moving on to, do y'all remember doing these sign tests whenever y'all were solving the polynomial and rational inequalities? Yeah, okay. All right. Example 3. Find the open intervals on which the function shown in the graph is increasing and decreasing. Where is this function going to be increasing? This is a graph of the function, so it's increasing. Let's do this. A. It's increasing on the interval from negative 8, not infinity, to negative 2, union 1, 2, 4, nope, 8. See, it's increasing right here. As long as the pen is moving up, this graph is increasing. It's still increasing. It has a point of discontinuity, but it's increasing everywhere here. It didn't switch to decreasing anywhere. All right, everywhere I have highlighted in red, this thing is increasing. It's decreasing from -2 to 1, right? All right, looking at the graph only. Identify the function's local and absolute extrema values, if any, saying where they occur. So we have a local, let's do the maxes first, of 4 right here, and right here at x equals -2, and a local max of 2 at x equals 4. We have an absolute max of what? Of 6 at x equals 8. That's going to be this highest point right here.
I thought it was still going.
No, it's only on this closed interval. Okay. Do we have any local mins? What is our local min? -2 at do we have any absolute mins?
Another local name. Or, yeah, it's that 8 negative.
I don't know that I would call that a local min because you don't know the graph to the left. It's absolute. I don't know that I would say this. Local means you got to look at the left and the right. Okay. And this is not an absolute minimum because I've got points that are lower. But do I ever reach an absolute lowest of -4? No, because there's an open circle there. This graph is never equal to, y is never equal to -4. I can go to -3.999999999, as many nines as you want, but you can never say -4. Okay? So that's all we can do with this graph. Example 4, for the function f of t equals 54t minus 2t cubed on the domain from -4 to infinity, do the following. First, identify the function's extreme values in the given domain. When it says find the extreme values, what am I looking for? Which means I need to do what? Take the derivative. So, the derivative of this function, f prime of t, is going to be equal to 54 minus 6t squared. To find the extrema, I set this derivative equal to what? So I have 6t squared equals 54 because I set the derivative equal to 0 to find the extrema. Extrema just means maximum and minimum values together. Kind of like siblings means brothers and sisters. Okay. One word gets it all done. All right, so t squared is equal to 54 divided by 6 is 9. T is equal to plus or minus 3. Don't forget, when you take the square root of a variable squared, you get two answers. 3 squared is 9, but -3 squared is also 9. Right? All right, looking at this domain, are both of those points in this domain? Yes. So we need to make a chart and figure out, because that was part A. Part B says which of the extreme values, if any, are absolute. Well, let's make our chart first. Arrow. Just get in the habit when you do this. If you find critical points, you know that you need to make this sign chart. And another one. Alright, so the first interval is going to go from -4 to -3, -3 to 3, and 3 to infinity. Why did I start this at -4? That's where the domain starts. Alright, so between -4 and -3 is -3.5. I want to look at where the derivative is equal, what the sign of the derivative is. Alright, -3.5 squared is bigger than -9. That's going to be bigger. This is going to be negative. The sign of the derivative here is negative, right? No. Yeah, okay, fine. I don't have this factored. Let me do this. Oh, here's the problem. This is going to be 6 times 9, that's 3 plus t times 3 minus t. This is easier to do when you factor it. Alright, so if x is -3.5, that's negative, that's that's negative, that's positive. Is that right? Yep, that's negative. That's positive. The whole thing is negative. The function is decreasing. Yeah, I made a mistake last semester. Alright. At t equals 0, this is going to be positive. The function is increasing. At t equals 4, this is going to be negative. The function is decreasing. Okay? Part B to this question says, which extreme values, if any, are absolute? Well, this function is going to go from decreasing to increasing to decreasing. I'm going to have to check and see what the endpoints are as well as critical points. So I need to evaluate f of -4, f of -3, f of 3, right? Mm-hmm. So go to the original function. Replace t with -4. And tell me what we get. Thank you. Replace t with -3. And with +3. Alright. Do we have an absolute minimum? This is going to be an absolute maximum, isn't it? At 3. Because we have a local maximum here. The shape of this graph is this. And because this point right here at 3 is higher than this point right here at -4, we're going to know that this is an absolute max of 108 at x equals 3. Do we have an absolute minimum? No. We don't have an absolute minimum because this is decreasing forever out to infinity. So we have a local minimum, don't we? X equals -3. So our local minimum of -108 at x equals -3. But we don't have an absolute minimum because of the shape of the graph. Part C says support your findings with a graphing calculator. This is why God gave us calculators. We type in our function, and our function is 54 x minus 2x cubed and when you set your window here, we should at least let the x start at -4, shouldn't we? Because that's where our domain starts. And let's go out to 4. And our x scale can be 1, that's fine. But when we decide on our maximum and minimum values, why don't we use -300 to +300? And we'll put a tick mark at every 100 so that we can get a decent picture. Probably should have made my x's go out a little further. There we go. So when we look at this graph, the important features that we have to remember are, first of all, our scaling. This is going to be at x equals 1, 2, 3. This is going to be -4, 2, 7. There's 1, 2, 3. This is x equals -3. And the y values are going to go from -300 to +300, and we step at every 100. Okay, so we've got a picture now that supports our conclusions from the calculus. That wraps up section